And my name is Zhenyu Liao, and I'm from University Paris-Saclay, France, so which is kind of in the country yard of Paris. And this is joint work with my PhD advisor, Romain Guyet. And this is about how to use random matrix theory to understand say, deep learning or deep neural network that are trained with gradient descent. So I start to realize after 2 days of workshop that we really come from super different backgrounds. So if you have any problem or questions, feel free to stop me, because I have about 29 slides, but I think 20 of them are just equations and calculations. So it's just the motivation and problem statement, and then finally the discussion are super interesting. So if you have any question, I can do it rather fast and skip all these main results. Okay, here we go. Motivation. So we are today in the so-called big data age, that we are constantly face a huge number of data and each of them are of large dimension. Okay, and we try to handle this data with super complicated, for instance, of deep neural networks, these huge learning systems. And more precisely, I mean, I would like to consider the number of data n, the dimension of data p, and the number of system parameters of my learning machine, big N. All these are large. This is a very practical setting, since when we do a computer vision task, for instance, of image classification, when we work with MNIST database or ImageNet database, we typically have NP both large, and in particular, N is not much larger than P, okay? It's smaller than 10 times P. For instance, with MNIST, we have about, here I'm talking about the number of images per class, because we're assuming that in this class it has a kind of distribution. So basically, we're dealing with images of about 784 dimension, so it's an image vector, and we only have 6,000 of them per class, okay? And it's the same thing for ImageNet databases, which are more, say, high-dimensional and large data sets. On the contrary, or on the other hand, we really use huge systems or machine learning stuff to treat this data. In particular, we're using the so-called over-parameterized deep neural networks, where the number of parameters of these deep neural networks, big N, is much larger than, say, 10 times the number of the data. Take the example of the kind of shallow and out-of-dated LeNet, which is only 5 layers, okay? Already we have a big N that is 10 times the number of data in each class of ImageNet. And this gets even worse when we consider much more modern deep neural networks. We really have thousands and millions or even billions of parameters. So we really have huge learning systems. So I would like to claim that it is important to understand modern machine learning problems under this setting, where we have big N, much larger than small n, and small n is approximately the same order of P, because we're dealing with high-dimensional data. With those high-resolution images, the dimension of the data vector are large. And I would like to claim that under this regime, things are super different. For N and P, both large and comparable. Many classical statistic wisdoms breaks down, and our low-dimensional intuitions no longer holds. Here is an example of doing sample covariance estimation. In the region, I would like to call random matrix region, or the region where both N, P are large. So the number of data and the dimension of this data are both large and comparable. Okay? We're trying to estimate the population covariance from some samples or from some data. Assume that the data are just random Gaussian vectors of some population of true covariance, say. And we would like to try to estimate this population or the true covariance from n samples. And so n data vectors, and each of them are of dimension p. Okay. Things my data vectors are Gaussian distributed. We know that the optimal maximum likelihood estimator in this situation is the sample covariance estimator, or the sample covariance matrix, which is this C hat. Okay. So it's given as a sum of n rank 1 matrix. This xi transpose are rank 1. Okay. So it's of rank at most n, and it's believed to be optimal when, say, n goes to infinity with p fixed, or n much larger. So the number of data much larger than the dimension of the data. But when we consider the region where n, p are both large and they are comparable, apparently this is no longer true. I mean, the sample covariance matrix is no longer consistent in the sense of operator norm or eigenvalue. And we'll say an eigenvalue mismatch, because a very easy example is that consider we have a true covariance matrix equal to identity. Okay, we have a population covariance equal to identity. And then consider the extreme case where the number of data is smaller than the dimension of data. So n is smaller than p. And in this case, our sample covariance matrix is not consistent in the sense of eigenvalue, because it must contain at least p minus n 0 eigenvalues, while the true answer of my population covariance is all equal to 1. So all its eigenvalue, all the true eigenvalue is equal to 1. So we have an eigenvalue mismatch because of the rank problem that I just mentioned. Okay? So apparently it's not working for when I do not have, say, kind of enough data, or my problem, my data dimension are kind of large. This is not working. So here I talk about, and I would like to claim that it's typically what happens in today's modern machine learning stuff or deep neural networks, because we are trying to use a lot of data. So I agree that ImageNet, we have a lot of data, but each of them are of high dimension. We have about, I don't know, 400 times 400 times 3 colors. Each of those data are of high dimension. And even more, we have a super, super large statistic model, for example, of residual networks that contains a lot of parameters. Basically, we are trying to fit an enormous statistic model with a large number of, but not really sufficient number of data. And if we want to...
The limit you're doing with n and p diverging.
Yep, linear.
You're doing a canonical way, meaning the ratio's 3, but so
linearly.
you're really doing one limit.
Yeah, exactly.
You fix the ratio, then you take a limit.
Exactly. Okay, so basically I would like to claim that if we want to understand why deep learning works, we should understand how things behave in this scenario, in this region. Okay, so since I have been talking about the eigenvalues, well, we have some results on eigenvalues in this NP large limit. So I just talked about the extreme case of n smaller than p, but you will say, okay, perhaps we never see this in practice. I mean, we always have much more data than the dimension of the data. So I would say, okay, how about n equal to 100 times p? We have 100 times the dimension of the data. And perhaps you will say, well, it seems to be large enough. I mean, it seems that we have sufficient data. Well, I would say it's not really true, because we have some random matrix series tells us that if we again consider the eigenvalue in this case, in the case of our population covariance is the identity, we know that it's going to go to in the large NP limit, it's going to the Marchenko-Bastard law that Michael just talked about early in the morning. And I would like to say it's really a close fit, because I have only p equal to 500, and we see the histogram of my eigenvalue of my empirical estimator. It's really get close to this limiting distribution of Marchenko-Bastard law. So even for 500, it seems to be asymptotic. It's really close. We have a close match. But the main message is here that in the equation of Marcinko-Bust law, we see that all the eigenvalue of my sample occurrence matrix will be spread around the interval between lambda minus and lambda plus. And in the particular case of n equal to 100 times p, so that's my factor c here is equal to 0, 0, 1, okay? Perhaps we think that with n equal to 100 times p, we have already sufficient data, but in fact, we are indeed making a minus and plus 20% error because the population eigenvalue is equal to 1. And the range of all my eigenvalues is between 0.8 and 1.2. So we are indeed making a plus and minus 20% error in the sense of eigenvalue at least. So even with 100 times the dimension of data, it's still better to consider that we are in the region where NP are both large, but not only in the limit of n large and p fixed. So this is the motivation part. And I think I convinced you that even we have kind of huge number of data, we should consider to work under the theoretical framework of random matrix theory. Okay? And now I will talk about deep learning. So every time when I try to start with this slide, I get kind of nervous because I'm not doing deep learning.
Models that are consistent in that limit. So if you say the model's a delta spike at 1,
yes,
you get the spread.
Yes.
And presumably, if that delta spike is spread out slightly, the spread is spread out slightly more.
You mean the Marcinko-Bust law,
Yeah.
or?
I mean, could you come up with a distribution where it's spread out in just the right way, such that in this limit, n over p is 10 or 100?
I didn't
get a
get
consistent result in the limit?
Okay, say if we can really consider the Marcinko-Bust law is fixed by this coefficient c. So for c fixed, we have this interval fixed. And if we consider, for example, heavy tail stuff, I'm not super expert for that, but perhaps there's something to do. Okay. Okay. So yeah, I will try to start deep learning, but I'm not really doing deep neural networks because, well, basically I do deep neural networks works with only one layer. So I'm basically doing linear regression. But I'm super happy because I see many guys here are also doing linear regression. So pretty okay.
So you do deep neural networks with one layer
Yeah.
and no nonlinearities.
Yeah, exactly, linear one. Okay, so still deep networks is a motivation. We know that all these deep neural networks are trained with backpropagation or basically gradient descent, and they work super good in practice. In particular in image classification, I guess. But there's the so-called generalization mystery. Things, again, we are doing over parameterization. We have a super huge number of parameters for our networks. Basically, people use, in classical statistical learning theory, believe that in this scenario, we will always have a generalization problem for our models. I mean, if the model is super large, okay, say for a given set of training data, or for a given set of problems that has kind of structural distributions, we have a model complexity that is fixed to this problem. Meaning that if you consider a larger family of models that contains this particular correct models as a subset, it is often difficult to find ways to find this good subset unless you use some regularization techniques, for instance. So basically, if you use super large models, it is not easy or not evident to find a good subset that works on your problem. Okay? But the mystery is that, okay, for almost all problems, for MNIST, for ImageNet, or what kind of problems, once you do super large deep neural networks, work super well in the sense that there is no overfitting and it's generalized well. And it works just pretty good. And we don't understand why. And in this work, I would like to try to answer the following two questions. So first of all, why over-parameterization will not, in this scenario, or in the scenario of at least a linear regression, will not harm generalization performance. And in particular, another important aspect is that why by doing gradient descent to get our model will also contribute to the generalization of the performance of our model. And how to answer these two questions, I will propose a general random matrix framework to analyze that those basically simple neural networks are basically linear regressions that are trained with gradient descent. And the conclusion finally will be that both doing our parameterization, so having a lot of number of parameters, and the fact that we are using gradient descent to get these models will help us to generalize better. Okay, so we're going into detail. And more concretely, my object will for example, on the MNIST data set of two numbers, 1 and 7, I would like to predict its performance as a function of the time that we're trained on, okay? So t is just the time, or you can say the number of steps that we're doing gradient descent. And I would like to predict its performance as a function of the time of my classifier, of my linear regression, or for my simple neural network. So here's a training performance or training misclassification error rate, and here's the test one, okay? So we see that for the test performance, it goes down and then goes up a little bit. So there is a kind of overfitting in this figure. And my objective here is to understand why we have these two curves and how can we predict the performance of this simple neural network. Okay. So equations. I'll be working with this data model. So I will be working with a mixture of Gaussian of two classes. Okay, we have two classes with different means and covariance, and for each, and I would say it belongs to class A, class 1 or class 2, with different labels of minus and plus 1. Okay, so I have a mixture of Gaussian, and I would like to use my neural network or linear regression to classify or to separate this mixture of Gaussian and to understand the classification error rate. And I will use gradient descent to learn my simple linear regression problems, okay? I have my data X and they are associated label Y, and I want to learn this classifier W by minimization this quadratic error. So basically, it's a linear regression model and this convex model. So if you train to infinity or train to convergence, you will get the least square solution. Okay? But I want to understand all the performance as a function of the time you train on. So I want to understand, okay, so basically for this problem, for a small enough gradient step, we can consider the associated gradient flow given by this differential equation. And it has nice closed form so that we can write our classifier, so W, as a function of t that depends on my data, my training data, and the label or the least square solution finally, and the training step and t, etc., and also the initialization, W0. So I have a closed form of my classifier, and I just want to understand the performance of this W as a function of t. Okay? And we see that, just as a remark, we see that we have an exponential of some kind of matrix, and that times the initialization, meaning that we are from the initialization that goes to the least square solution at an exponential rate. Not yet, but I will show it. By consider the different ratio of NP, in fact. We'll see that. Okay. So I have a nice closed form solution, and I'm trying to work on it. Okay, so here is our key object. We want to understand the performance of this classifier on my problem. So just to recall the exponential of a matrix. So it's basically keep the associated eigenvalue unchanged, and I take the exponential of the associated eigenvalue. Okay. So here is the definition of the matrix exponential, and we see that, well, indeed, our object is kind of a projections onto the eigenspace of our sample covariance-like matrix XX transpose of my data associated that are weighted by the exponential of the associated eigenvalue. Okay? So it's a kind of function of my sample current matrix projected either on the initialization or on the least square solution finally. So it seems to be a rather complicated object to treat, but we have an answer with random matrix theory.
Which way are you rectangular right now so far?
Sorry?
Which way are you over constrained or under constrained? Which way are you rectangular right now, or does it matter?
You mean the dimension of x, right?
Of x,
It does not really matter. It converts to the same solution under the same form. And really thanks to the talk of Mark, we are going to use some Cauchy's integral formula and resolvent techniques we'll see in the next slide. So we have an answer to this problem. Okay, so test performance, I would like to understand for new data from one of the two classes, the misclassification probability, okay, of my classifier W as a function of T. So since I have my new data independent of all the other training data, and it is basically Gaussian, we condition on this WT, we get a Gaussian random variable. And our object is just to understand this W transpose mu A and W transpose CAW. Okay? Once we understand these two objects, we have our classification performance as a function of T. And we're happy. Okay? So what do we do? We use Cauchy's integral formula. Because we're treating some kind of exponential of the eigenvalues of my sample current matrix, we'll use Cauchy's integral formula to rewrite as a function of the resolvent. So which help us understand to simplify the problem. And in the second step, things for random x, so my data are random Gaussian, so we have a x are random. So all these guys, all these quantities are indeed random, but they are asymptotically determinist in the sense that when the NP goes to infinity, they are close to some determinist quantity with probability 1, almost surely. So we can capture this determinist behavior in the NP large limit with the so-called
The time or the NP?
NP. I'm not talking about time. It holds for any t.
So in the limit, the ratio is constant.
Exactly. It's during the so-called random matrix reading. Okay? And we can do this with the so-called determinist equivalent technique. So when I say it's asymptotically determinist, I mean that it only depends on the data statistics, on the mu of my mean, mu and covariance CA, and the problem dimension. Okay? So once we get the result, it helps us understand at least how gradient descent affect this linear regression problem. So the conclusion is that for this classification problem, the classification error rate at any time is asymptotically determinist. And we can predict it. And it approximately holds for a non-symptotic MNIST data set, as we say. So main result. Cool. Again, we have this formula of, so it's basically the mean that we are interested in. And we're doing Cauchy's integral formula. So again, I recall, for a complex analytic function fz, we can do a contour that circles around the pore of this function so that we can write fz0 in a form of contour integration. So it's just a technique to write some kind of, say mathematical object in a more convenient way, okay? So this is for kind of scalar versions of Cauchy's integral formula, and I'm going to do the matrix form. Okay, so consider this guy, this mu transpose WT. For WT that contains kind of exponential and identity minus exponential of my sample current matrix. Okay, so we are interested in this form, which is indeed some vector A transpose exponential of a matrix times B. Okay, so it's a scalar, but it contains some matrix exponential that is not easy to treat. We can use spectral decomposition of A, which is basically the definition of the matrix exponential. We have all these eigenspace or these eigenvectors. And we can use Cauchy's integral formula on this exponential function. So where we introduce this lambda I A minus A. And here, all this, my circle, my contour should have circle around all the eigenvalues of my matrix of interest A. Okay? So I just rewrite in the form of contour integration, and I continue. I just move in this sum, and I find the definition of the resolvent. Okay? So it's QA, which is defined as the inverse of A minus A times identity. Okay? So basically, for FA, which is our object of interest, we can write in the form of contour integration, and we get out this difficult exponential function, and we are left to treat only this A transpose QAB, these quantities, where QA is the resolvent of my matrix of interest A. And for this contour, I have to circle around all the eigenvalues of A. Okay? So just a technical reminder, the exponential function is super nice to treat with. I mean, it's a complex analytic, and it's single value, and most importantly. If we are working with other kind of functions, for example, the exponential log, well, it's multi-value, so there is possibly the so-called problem of branch cuts. But in this, at least in this sample, we're happy. But if you are working with other kind of complex functions, you should start to pay attention and worry about it. But exponential is super cool. Okay, so now we use Cauchy's integral formula to rewrite our problems, but it's not yet solved because for A random, so basically A is my sample covariance matrix here, okay, 1 over n XX transpose. And I'm left with A transpose QAB for A random. So I have claimed that basically, asymptotically, this guy, so this FA will become determinist. So, which means that this A transpose QAB will asymptotically determinist. But how can we capture its asymptotic behavior? We have the so-called determinist equivalent techniques. Yes, please.
So maybe I missed it, but the eigenvalues of X transpose or XX transpose are real, but you still treat them as complex.
No, they're real.
But so you say Z is in complex, is that?
Yeah. Okay. So lambda IA, they're real values. Okay? So for example, the exponential of a real value is a real value, but I can write in the form of contour integration. I introduce Z.
So you still treat them as a complex
They're real.
with a zero complex.
Yeah, with a zero imaginary part if you want. But they're real, they're on the real line, they're on the complex plane, and I would like to circle around them, that's all. Okay? So to understand the asymptotic behavior of my FA of interest, I have to handle this random guy, okay? It's random variable because our A is random. So we have a so-called determinist equivalent technique that tells us that for a random matrix A and its resolvent QA, it has a so-called determinist equivalent of the resolvent QA in the sense that asymptotically, this normalized trace of this two guy, so a random resolvent and its determinist equivalent, as well as a bilinear form of type A transpose QB, goes to 0 with probability 1 asymptotically if B, A, B are boundary norm. Okay? So basically, this idea says that, well, when you are we are dealing with all these A transpose QB, which are random quantities, you can just consider its determinist equivalent counterpart for NP large. And in particular, in this case, so we have this bilinear form of my resolvent. We can it will go to, or approximately go to, its counterparts that are replaced with its determinist equivalent. But how can we compute this determinist equivalent? We'll show that. Okay, so basically we say that once we use the contour integration to write our object of interest, it will admit an asymptotic determinist limit that can be used.
Will it not be sensitive to Z? You also have dependence on Z?
Which Z? Yes, this.
In the integral.
in the integral, this
The
one?
deterministic equivalent is for a fixed random matrix, but the random matrix will also depend on the Z.
No. Okay, so I do it again. For a random matrix A,
I understand that.
yep,
Okay, but then you have the QA.
QA is a function of Z.
Right, so we have those two assumptions, that is QAZ.
QAZ, you mean this function?
In those two bullet points.
I think does Q bar depend on Z?
Yeah, Q bar also depends on Z. Q bar is a function of Z. So here,
Right.
Q bar is a function of Z.
I'm just trying to understand these things. This is a limit for all Z's or?
Yeah, for all Z's
Okay,
that are
okay.
not eigenvalue, that not are close to the eigenvalue of A.
So it's kind of uniform in Z.
Exactly.
Okay.
Sorry.
'Cause I don't see Z written there. So I guess
Yeah, it's not super
Okay.
clear. I agree, but yeah, you're right. Okay, I continue. So basically, we'll talk about how to compute this deterministic equivalent in I think in 2 or 3 slides. But the intuition behind this is some kind of matrix random vector or matrix concentration technique. So basically, if we consider a random Gaussian vector of dimension p, and we do an observation that maps from Rp to R, we'll say that this function fx, which is a real value or it's a scalar, will concentrate around its expectation or its mean with high probability. Okay? So when we do an observation of my random vector, it will concentrate around its expectation. And this happens also for random matrix. Okay, so it's dimension free. And if we consider a random matrix that has many random vectors, independent random Gaussian vectors, typically we'll add a factor n here. So by letting n goes large, we'll reach something goes to 0. Okay? So we'll arrive at an almost sure convergence R with probability 1. So basically, for kind of random matrix, so here is holds for Lipschitz function. And it's basically the same thing here. So when we do a linear function or Lipschitz function observation of my random matrix A, we'll say that, well, this random guy is also going to concentrate around its expectation, since QA is random because A is random, okay, with high probability. And we can make this with probability 1 by letting NP go to infinity. But in practice, this QA is not accessible. I mean, we cannot compute it even when we know the distribution of my random matrix because it gets involved in high-dimensional integers. But they do admit a kind of asymptotic equivalent in the sense that there's a determinist matrix QA bar that's asymptotically close to this exponential, the expectation, sorry, asymptotically as NP goes to large. Okay? So basically, and this QA bar is, we can compute it efficiently with, for example, solving polynomials or basically fixed point equations. So we know that this random guy will get close to its expectation as NP goes large, and this guy will get close to its QA bar counterpart asymptotically also. And with all these two ingredients, we can get an almost true convergence. So it's just the intuition behind it. It's a concentration phenomenon. Yes, please.
So you start with regression, right?
Yes.
Then you switch to classification.
No, I'm working on it. So I'm working on a classification problem because I use a mixture Gaussian model. But I use regression to do
Well,
this.
this is exactly the disconnect that I don't understand. Seems like a mismatch between the model and
Well,
what you try to do with this.
Yeah, I agree. So basically, we can do regression problems. We can show that the expectation risk will going to be the same thing. But since I'm working with MNIST data, which is basically for classification, I think it's more natural. So I use linear regression model to do classification in this case.
Yeah, could you do similar analysis for
Exactly.
regression?
Regression also,
Okay,
it holds.
fine.
No problem. Okay, so this intuition behind this so-called deterministic equivalent. And we have finally, after these 2 steps, a sort of central limit theorem. So basically, so how do we get this? We plug in this is a Cauchy's integral formula and replace this complicated exponential with its resolvent. And we observe we have a bilinear form of my resolvent of some kind of random matrix, and we just plug in our determinist equivalent to replace this guy, okay? So with these two steps, we get an CLT, which tells us that basically for new data, the soft output of my classifier will going to be a Gaussian random variable in the limit. That its mean and variance are given in the form of contour integration, and depends on the data statistics of mu1, mu2, c1, c2, and the dimension of the problem and the gradient initialization. So the formula is kind of ugly, but generally it tells us we have a central limit theorem at the very end. The problem is that how can we compute all this determinist equivalent, QA bar, okay? I have said that they are computable, they are in practice computable with fixed point equations for genetic covariance CA. So basically, if we want to compute this Q bar, we have to use this CA and also a higher probability in each class. So we have to know both class, the covariance in both class, and we have to do a fixed point equation because this Q bar depends on GA, that depends then on Q bar. So we just launch this fixed point equation and it will converge, and we can get the equation of get the expression of numerically we can get Q bar, okay, for all z. But the problem is that it's not easy to understand if the genetic covariance CA. But we have a very easy formulation that again appear Marchenko-Bastor equation. So basically, if we consider the special case where all my covariants are close to identity, we have a closed form solution, which are no longer fixed point equations. And my Q bar are proportional to identity, which is easy to say because my covariants are just proportional to identity. So it's identity minus something times identity, and inverse is going to be proportional to identity. And the MZ is the so-called Stieltjes transform of my limiting distribution. Okay? It depends indeed on the spectrum of my sample occurrence matrix. But the good thing is that we have a closed form. I mean, we have an expression of MZ that depends only on Z and C. C is the ratio of my ratio Pn, okay? It depends on the dimension problem. So in this particular case, we have a closed form solution, which is super cool and can help us understand many things. And more concretely, if I plug in my determinist equivalent, we'll get the expression of E and V. So it's again a CLT, and I get my expression of E and V that are explicitly, okay, the closed form, but still in the form of contour integration. So
you had two values for MOZ, didn't you? The square root?
Yeah,
And
exactly. I choose the MZ that matches this condition. So basically, if you define a probability measure, which is basically the spectral measure of my covariance matrix, we can define its associated Stieltjes transform of this measure, and it must admit this, this equation. So for a given z, there's only one of the rules that works. Okay. We have this super ugly equation that are given in the form of contour integration, and it tells us something, but not easy, interpretable, or understandable. Can we do better? Okay, so this is a CLT, and this is just the corollary, the test performance. Since it's a Gaussian random variable, we can given the test performance using the Q function, which is the tail functions of Gaussian random variable, okay? But they are not easy to understand. Can we do better? Yep. We can do simplifications. So things we are working with any contour that circles around all my eigenvalues. And in the large NP limit, I know exactly all these eigenvalues are. I mean, I know exactly the location of these eigenvalues with probability 1 as the NP goes large. Indeed, it will going to be some kind of Marchenko bus store-like within some kind of interval, and a spike here, okay? So if you can say it, some isolated eigenvalue that contains information because I have some kind of mu, in fact. Okay, so it's indeed a spike model. Here I plot the eigenvalue distribution for NP that are not super large, but we see that it's again close match to the Marchenko-Bastor distribution. And we can also predict exactly where is this isolated eigenvalue as a function of my probability setting, okay? As a function of the mean that are trying to separate and the dimension ratio of my problem. So we know that with probability 1, they are there. And the question is that when we plot on complex plane, we're free to choose a contour that circles around all these guys and makes us happy to do simplifications, okay? So basically, I will choose a contour that circles around the Marchenko-Bastor distribution, the bulk, so this part, and use residual calculus to treat this isolated eigenvalue because I know that there will be a distance between these two because I know the location of both, okay? So we can choose the contour that makes us happy and do simplifications, and there is the result. Instead of doing contour integrations, we have very simple integral here. With mu dx, the Marchenko-Bastor law, and the nu dx that depends on lambda s, which is an isolated eigenvalue, okay? So indeed, this only mu dx contains information. Okay, but there are formulas, they are super ugly. I just want to show that it works for MNIST. I mean, when we apply our theory, so here is a simulation on MNIST data set as a function of the misclassification error rate as a function of time. And here's our theoretical prediction. When we compute empirically the mean and the covariance of MNIST and apply our theory, it seems to work pretty well because there seems to be a good match between theory and simulation. So it seems to work for MNIST, at least for these simple problems. But there are more important insights, okay? I want to do some discussions on generalizations and overfitting. So just a simple calculus again with Cauchy's integral, with Cauchy-Schwarz inequality to show that the optimal performance is given by this quantity. And if we let t go to infinity, which means that we are going to train infinitely long and converge to the least square solution, we see that the performance will drop by a factor of 1 minus mean c 1 over c, which means that we have a problem with performance problem if we use the least square solutions, okay? And this drop off, yes, please. Okay. Okay. And this performance drop depends on the ratio p over n. And if we consider that n, p are approximately the same value, this will give n, so it's given to be 0. So we have a serious problem if n are close to p. Means that if you use the same number of training data as your data dimension, the least square solution is not working at all. And I have a figure for that.
That's why the neural tangent people in that limit are fine, because they go to the limit where that gets...
Well, I'm not pretty sure about that. So basically, neural tangent people, I think they are working with infinite width and they can do multi-layers. So it's not, I'm not sure it's exactly the same thing.
Something with one layer, but the ratio got large, so that... Maybe
Avoid this problem, you mean?
Pretty similar, I thought.
Okay.
Because they're in that limit, and they sort of flatten out, probably because they don't go up because the
Okay, I see.
Is 0 or 1, whichever it was.
Yeah, it's possible. Good point. Yeah, so here I plot the classification error rate as a function of my ratio psi, okay? And we see that we have a singularity when n equal to p. This is super weird if we consider it, because for a given p, if we have a lot of data, we have n super large, then we go this side, and the ratio goes to 0. So we have a pretty good performance. But if we have more data, so this will go right forward. We have more data. When it gets close to the same value of the data dimension, it's not working at all. But if I have, okay, sorry, excuse me. So if we have super large number of data, it's in this limit point, okay? And if we decrease the number of data, so when with smaller, for a fixed p with smaller n, this ratio increase, okay? So if we decrease the number of data for a fixed problem, we'll see that when we decrease the data, first the performance not working at all, super large error. And then if you continue to decrease, it starts to work. So this means that at this point it's not working at all, but you still have less data. If you give less data, it starts to work. Well, it's not as good as if you have infinite number of data, but it's much better at this point. It's much better than this point, even if you have less data. It's super amazing. Okay, so basically for least square solution, so this conclusion holds for least square solution. And we see that we have a singularity. And many people who do overparameterization theory say that in the case of least square, we are in fact learning some vector W. And in this case, the number of system parameter big N that we introduced at the very beginning of my talk equal to P. And they say that, well, basically, it's a kind of benefit of doing overparameterization because here, for a fixed N, if you consider P goes large, so you can say the dimension of data goes large, or you can consider the system parameter goes large. If you're doing overparameterations, you increase this ratio, say, and you are doing better. Okay? Yes, please.
What? So this plot is plotting the function on the right, or it's plotting a function that...
It's a misclassification error rate, so it's a Q function of this guy.
So
Which is the Q function is a decreasing
what
function.
is the value at
1.
1?
Yep.
Do you have a value at 1? Is that a finite value? What do you get?
So basically, if you say get to 1, this mean goes to 1, and 1 minus 1 gets to 0. So it's Q of 0, which gives 0.5. You get my point? I repeat it again. Yeah, it's not diverging, even if we say equal to 1, because it's Q function of 0.
I see.
Okay.
Sorry, I think I missed a lot of parts. So your question is that so you are dealing with regression. So how do you do regression for like MNIST?
No, I'm using linear regression model to do classification.
Yeah, but how do you do it for like MNIST? You show some result for MNIST as well.
Yes, I show some result for MNIST. So basic.
10 classes, do you just use that first?
Yeah, I
class
use
or
2 of the 10 classes, sorry.
Oh, you need 2 of them?
Yeah,
So my second question is that since we are talking about overparameterized.
Exactly.
Yeah. So here's basically your overparameter is like basically your P, so your number of data is N.
yeah. No, okay, so I do it again. I'm not super agree with what people said because people say that, okay, so in the case of least regression, LS regression, in this case, we have the number of parameter n equal to the dimension of the data p because it's only single vector, okay? And people use this as an argument to say that, well, since we have a singularity of my performance, it's better to let p go large, which they say equal to have a larger system. Personally, I'm not super agree with that. I think there's just special case in the linear regression. But they use a theoretical argument to say that it's better to do overparameterizations. And they use this case. I'm not super agree with that.
So you have a continuous time model to do all this beautiful analysis.
Exactly.
And so, of course, we'll run this with the discrete time model.
Exactly.
Which you can view, I think, as what we numerical analysts would call an Euler method discretization.
Yep.
Where the learning rate is the time step.
Exactly.
Euler's method.
Exactly.
So do you, and then you can analyze convergence, and there's
Well,
theory for how Euler's method converges to the underlying differential equation.
Sorry, I didn't get the point. Once you have the gradient flow,
Yeah.
You have the differential equation, you can do discretizations.
Right.
But- yep.
But you can, but usually we think of we execute the discretizations.
Yes.
Numerical analysts do discretizations to approximate the continuous world.
I agree.
You're doing your
I'm doing
discretization
continuous
is the real world, and your
Yeah,
continuous
yeah.
time version is an approximation to that.
Exactly.
But you can use the same theory either way
I'm not
to bound the difference between the two.
I'm not pretty sure. You mean I start with directly with a discrete version? Is that what you want to say?
Well, so you would run the discrete time version.
Yeah, I agree. It's practice.
And so you want to know, does your model really agree with what happens in
Yeah.
practice? Or for example, for what learning rates
Yeah.
could you expect this to be an accurate
Yeah,
model?
yeah.
Because one potential place where this kind of paradox might get resolved is if you find that the learning rate, a certain learning rate doesn't give you a good approximation between the discrete and continuous time models, for example.
Okay.
And you'll find that by looking at convergence theory for Euler's method, which is actually not that hard as long as you have a Lipschitz constant.
Which paradox, the spike? Or
Well, the
we
sense
see
that
we see that in discrete cases also.
okay,
So
yeah,
this
so maybe
is-
there's no paradox, yeah. But
So basically, you mean that in practice we do not have this kind of phenomenon, or?
I don't know.
Okay.
No, I'm just saying.
Yeah, perhaps there. Yeah, it's a good
You
thing
could
to
learn
do.
something by looking at the convergence.
Okay, I got it.
And that will, and maybe what that tells you is that this is in all regimes a perfect model.
Okay, thanks. Yeah, so basically people use, any other questions, yes, please?
It looks like you don't consider regularization, but if you do SGD, or there will be an implicit regularization.
Yeah, that's true. Okay, so here I'm doing full batch gradient descent. I don't know what will happen with SGD, but within the same framework, I can do L2 regressions. And I'm not pretty sure what will happen, but
I don't think there will be a spike.
if you add L2
Yeah.
regression, yeah, perhaps I didn't take the formula. I'm not sure. Okay, so this is just kind of background that people use an argument to argue that doing over-parameterizations in the context of neural networks works fine because we have this decrease of misclassification error rates. But personally, I'm not super agree with that. But what I show, any other questions? Yes, please.
One more question. So you say, so why do you not agree with the popular explanation of?
Because I think it's just by chance that P and big N are same in this context. I mean, in general, I don't think they have proved this kind of result that go far beyond least square solutions.
When they do over-parameterization, they always do regularization, even in.
No, that's not. Yeah, I agree. But we're not.
This peak is sensitive. I mean, you may have it with a ridge term, but it's certainly sensitive. What they see is this goes down, and so what this shows is that on the left side you get a U shape, and on the right side it goes down. So that's, in a sense, goes to a corner case that the neural network people might not consider, but it still shows why you get the U shape in one regime and the down shape in another regime. And of course you can destroy it by putting on too much regularization, but it shows you get both.
Yes.
So are you saying this is a totally unique phenomenon to least squares?
I'm not sure. I have no idea. So I have no answer to your
Because
question.
nobody's, I'm pretty sure nobody's claiming that this proves anything for neural networks.
Exactly. That's
Right?
a
So
problem.
We're kind of talking about
Yeah.
phenomenologically.
Yeah, exactly.
So do you think it's a different phenomenon?
Personally, I think this holds only when you consider this kind of linear regression model, or if you add some kind of random features, I think it's going to hold. But I don't think if you kind of cascading more neural network, I don't think this still holds, or at least I have no idea how to prove this kind of stuff. I mean, there are empirical observations that they observe this kind of stuff, but I don't think it's exactly the same thing happens here. Or basically, I have no idea why we have this peak here indeed. I'm not sure. So I don't know. So these are formulas, but I don't know where it comes. I mean, it's because we have too many eigenvalues of sample occurrence matrix that are close to 0, but not exactly equal to 0. I have no idea where we have this singularity point, in fact.
So someone mentioned implicit regularization. So I guess
it's a good point. We can try it, but it's
So here, I mean, there's many notions of implicit regularization. I mean, I would argue in some sense that this picture, you know, on both sides of this picture you can see, or at least on the right side of the picture,
Yeah.
you can see implicit regularization in some sense.
Because?
Already, because if you have, I mean, if you have over-parameterization and you have whatever, you know, training model you have to
Yeah.
find a solution, since there's many solutions,
Exactly.
your model has to choose one of them.
Yes. So it
And
depends on your fashion to get your model.
Exactly, but whatever the model is doing, if the curve is decreasing, there's some implicit regularization
Yes.
that's happening.
And what I want to argue, this implicit comes from gradient descent. What I want to say in the next slide.
So we're a little over, so.
Only the last slide,
All right.
I guess. Yes, so people use this to say doing highly over-parameterization help do generalization, but here I show that for all t that is not going to infinity, so my classification performance is a smooth function of the ratio. So I do not, which is super different from least square solutions, okay? In what I'm doing here, well, we use gradient descent to learn a least square solution. If it's not convergent at any point of t, the performance is a smooth function of c, which means that we do not have this super weird singularity at z equal to 1.
And so what do you have instead? Do you have like a kind of a soft?
I guess we have a soft, so it will go up a little, but I mean, it's super different from going to, it's still working, but less good. So I use this as an argument to say that, well, indeed, if you are not doing linear or least square regression, and you are trained with gradient-based, before convergence or before, when you do early stopping, basically, before you get converged to the least square solution, the performance is kind of better, even if you do not do over-parameterization, even if that point stay close to 1. That's basically.
Train all the way to zero training error. Technically speaking, they are fitting the entire thing.
Exactly. So least square is not good. Exactly.
Oh, this is just the statement for least square. This last point you made.
So I have shown that if you train to infinity, you are doing overfitting. And overfitting, we have a problem when n is approximately equal to p. And here I want to argue that if you're not going to least square solution, if you do early stopping, early means that's not converge. It's pretty cool, and we do not have this singularity problem. So we do not.
So normally you have to stand up and pull the speaker off the stage, but now we have to stand up and pull all the questioners off the stage. So why don't we interrupt, and if there's questions, bring them to lunch. Otherwise, we'll be here till 2 p.m., but this is great.
Okay, thank you.